Okay, so we should have the habit of starting at the hour. So today's colloquium, we have pleasure of Gur Ari. He did undergraduate at Hebrew University in Jerusalem, graduated in 2007. Went to Weizmann Institute and did research on quantum field theory, quantum gravity, string theory, under supervision of Hirosi at the time, and then received PhD in 2014. And went to Stanford to continue his theoretical physics research as a postdoc. And what made gradual transition, he still continued to be postdoc at the Institute for Advanced Study in Princeton. But then after that, he moved to Google as a research scientist. And now he actually left Google at the end of last year, is starting a new company. And so, well, I don't think I need to do introduction. We all need to find out what our job lasts for the next 20 years or so. So please.
Thank you. Thanks a lot. Thanks for the invitation. Always glad to be at Caltech. I'll tell you about Minerva today, but because this is a physics colloquium and it's really a machine learning talk, I'm going to start by covering some background so that I hope the rest of the talk will be somewhat coherent. So I'll really start from deep neural network basics. And what do we mean when we talk about deep learning and deep neural networks? How do we build them? How do we train them? This talk is focused on natural language processing because we will end up talking about math and physics and LaTeX and things like that. And so the examples will be kind of tailored to natural language processing, but for now, these techniques are very general. You can apply them to language, you can apply them to vision and to many other, or to particle physics, many other tasks. So the basic object that we deal with in deep learning is a neural network. This network is, it's essentially a way of constructing a class of functions that take inputs out of some distribution and give us some prediction over what might be the next token in a sequence, or what might be an object that's present in a picture, or any kind of function that we want to calculate on the input. And the way we, in deep learning, the way we construct these networks is as a series of layers that are composed on top of each other. Every layer calculates some simple function. And together we have a composition of some complex function, where the main constraint that we want to introduce when we build this network is that it should be automatically differentiable. Because the way we're going to be training these networks is to say there are going to be all kinds of parameters inside the networks that we want to tune to make the function do what we want it to do. And we need to be able to calculate the gradient of some objective over these different tunable parameters, so that we can do gradient descent and kind of optimize the function to be better and better. And so the main constraint is we want to build a differentiable function, but other than that, kind of anything is on the table. So we're going to start with a very simple network, the simplest kind of network that people play with in this space. It's called a fully connected network. And we're just going to take this network and try to apply it to the problem of how do we build a model that looks at some piece of text and predicts what the next words in the text should be, and thereby sort of iteratively generating completion for that text. And so the basic setup, we're going to start with some vocabulary of tokens, some vocabulary sigma. And tokens for this talk, they're going to mean, roughly speaking, a token could correspond to a word or to a digit or to a mathematical symbol. Usually we learn what the best tokens are given some statistical distribution in our data. That's not really going to matter for what we're going to talk about, at least for now. So just imagine that a token corresponds to a word. And we're going to decide in advance what vocabulary we want to deal with, or what alphabet we want to deal with. And we're going to build a model that will accept a sequence of tokens as its input. And the output from this model is going to be a probability distribution. So the input is going to be this X, which is going to be a big vector with a length number of tokens times the dimension of our vocabulary. So imagine that every token is going to be some represented as a series of lots of zeros and one at the place where that token corresponds to the vocabulary entry. And then we're going to do that for every token. So that's going to be our long input X. And then the model is going to calculate this probability distribution P. So P is going to be what is the probability for every possible next token that the model assigns as like the best possible, or the probability that it assigns as the completion for the next token. It's going to be conditioned on all the previous tokens that the model saw. Okay, so that's the function we're going to try to train and get to properly model the text that we have. And then the actual function we'll start with is going to be this fairly simple function. It's going to be this fully connected network. So it's going to take the inputs, everything before the current token, and then it's going to apply a linear transformation W1. So W1 is going to be a matrix of parameters that we'll learn as we train the model. So there's going to be a linear transformation. Then we're going to apply a nonlinearity on every entry of the vector. Typically, we use as nonlinearity this thing called a ReLU function. It's simply what we have here at the bottom. It's going to be 0 for negative inputs and the input as is for positive inputs. That's all. And then we're going to do this again and again. Each time we're going to act with a new linear transformation W. And the dimensions of these matrices can change, they can grow, they can shrink. These are all choices that we can introduce when we're building our model, but this is going to be the basic structure. We're going to do this L times. So we're going to have a network with L layers. And then at the end, in order to get a probability distribution out of this model, we're going to apply a softmax function. So softmax here is basically take the model's output Z, which at the last layer are going to have the same dimension as our vocabulary size. So we're going to get a probability prediction for every possible token as the next token. And then we're going to normalize it essentially using a Boltzmann distribution. So Z's are going to be the output from the last layer. We're going to normalize them like this so that we have a sequence of zeros, of numbers between 0 and 1 that all sum up to 1. And so we can just interpret the output from this model as a probability distribution. So that is the basic setup. If we just set it up this way and we randomly initialize the weights and we ask the model, here's a chunk of text, predict the next token, is going to spit out some random distribution that's going to have nothing to do with the text. And so the next step is we need to train this model. So we need to continuously or iteratively tune the weights of the model so that it actually captures the distribution in the data that we care about. And that's the next step. So the way we do that is typically, we start by collecting a large data set of documents that we care about. So if we're doing natural language, maybe we'll collect sequences of text from Wikipedia, news article, books, scraping web pages, wherever we can find text. We will split them up into token sequences. And then given a token sequence, we're going to train the model. We're going to show the model, here's a bunch of tokens, let's say 100 tokens. Try to predict the next token. It will do what it does. And then we will come in and say, oh, the actual next token in the text was this. There will be some error. And then we're going to try to tune the weights a little bit to reduce that error. So we're going to turn this into an optimization problem. And concretely, this is how we actually turn it into an optimization problem. What we do is we say, okay, the model's output is some probability distribution. We also know the ground truth probability distribution, which is this next token was the actual next token and nothing else. So we have a highly concentrated ground truth distribution. And we're going to calculate the cross entropy between the actual ground truth distribution and our distribution. And we're going to try to minimize the cross entropy. If we can minimize the cross entropy, that means we're pushing the model's prediction closer and closer to the actual distribution we see in the text. And concretely, this is what it looks like. So we end up with a function that we call the loss. This is the function we're going to try to minimize, where if we do a good job minimizing it, we're going to end up with a model that gives us good predictions. And it's going to be, let's say we're doing this on a single sequence. For every subsequence here, x smaller than t, we're going to calculate the model's prediction, and we're going to evaluate the model's prediction on the actual token that we saw in the text. That's going to be xt. That's where the ground truth label comes in. And we're going to take the log of that, and we're going to take minus of that. That's going to be the cross entropy. And then we average that over all the different sequences that we have in the text. And what we end up with here is a function of the weights of the model, because we've already entered, I mean, it's also a function of the text, but in that sense, we just assume that the text is fixed once and for all. It is a function then of the weights of the model. And if we're able to sort of tune the weights of the model to minimize the this cross entropy, to minimize the loss, we'll end up with a good model, or that's the hypothesis anyway. And the way we do that, the way we solve this optimization problem is using gradient descent. So we set up this whole function plus the log and everything so that we can easily automatically calculate its gradient with respect to the weights. And so now we're going to do gradient descent in order to decrease the loss. And the most basic version of gradient descent, or this is the gradient descent algorithm, is to say, okay, at every step, we're going to take our huge vector of weights that sort of flattens out all the different weights that we had in the network from all the different layers. We're going to calculate the gradient of the loss with respect to this. We're going to choose some coefficient here that we call the learning rate, which is going to control how big training steps we're going to take. And we're going to take a small step in the opposite direction so that we're rolling downhill because we're trying to minimize the loss. And we do this again and again and again. So first step, we calculate the gradient, update the weights a little bit. Then we're at a new point in weight space. We calculate the gradient again and repeat and repeat. And if all goes well, we'll end up with a set of weights where the loss is low and we have a good model. So that's how we train these models. And now we had our trained model, we want to use it to actually generate some text. And this is how we do this. So let's say we are given a new kind of context, sorry, context here means input. We are given a new input sequence of tokens. And the way we actually generate text out of the model is token by token. So what we do is we compute the next token distribution P. So we give the model our input, our prompt, or context. We calculate the input distribution, and then we sample from it. And there are different ways to sample from it. The simplest way to think about this is that given a probability distribution, we can sample it from it with temperature. And so what that means is one way to think about it is to say, well, we renormalize all the probabilities using some inverse temperature beta, we get a new distribution and we sample from that. More concretely, we can say something like, well, if you want to sample with 0 temperature, that corresponds to always choosing the token that has the highest probability. And if we sample with infinite temperature, then we're just sampling randomly from all the different tokens. And there's a certain trade-off there in terms of how accurate the predictions will be versus how diverse the predictions will be that we'll get to later in the talk. But for now, we can just pretend that we are choosing the temperature somehow, and we're sampling from the model to generate the next token. And so this is effectively what this process looks like. Let's say we start with the input where we have a single token, the word the, and we want to start using the model that we trained to complete the sequence. So we take our input X, which is the word the, a single token, we calculate the probability distribution, we sample from it, and we got the result quick. So we take the second token, we add it into our input. Now we have the quick as the input, and we repeat. We feed this through the model again, get another probability distribution, and we get the next word brown, and so on and so forth. So this is how we can generate long pieces of text from a given input. All right, so that is the basic setup. And the main difference between what I described so far and what we actually do in practice is the architecture of the network that we use to calculate these probability distributions. We can do everything that I've described before. It just so happens that on text, that will not generate very good results. We want the architecture of the network to be better aligned with the kinds of processing we expect it to be able to do on text. And you'll see what I mean as we talk about transformers. But this part about having a vocabulary, taking a sequence of tokens as input, predicting the next one, training it using gradient descent, and then sampling again and again to generate text, that is all actually what we do in practice with just very few caveats. But the main thing that's different is that the actual network is not just a sequence of linear transformation, nonlinearity, linear transformation, nonlinearity. It's not just a fully connected network. It's something else called a transformer or an attention architecture, which ends up doing obtaining much better performance on text. And once we go through this setup, that whole setup is what's actually driving all the language models that you hear about, like GPT-3, Lambda, ChatGPT. It's all based on this architecture, and Minerva, which I'll talk about today. So up to this point, everything is the same. And the new thing I want to introduce now is this transformer architecture, which is now a stack of different layers as before, but we're going to have a new kind of layer, which is the attention layer. And you can think of this layer as introducing some kind of multi-body interaction between different tokens, and then fully connected layers, which are somewhat similar to pretty similar to the ones we had before, which act token by token. And so this is at a high level what a transformer based architecture is going to look like. Again, we have as input our T tokens. The numbers here correspond to the index of these tokens in our vocabulary. We're going to input them, we're going to pass them through a linear transformation to get these things we call embedded tokens. So this is going to be the basic unit of information that gets processed by the network. It's going to be number of tokens times D, which is some hidden dimension. This is the dimension of the vector we internally use to represent every vector. Then we're going to apply the transformer function, these different layers that we'll describe in a minute. And that's going to be the transformer output. And then we pass a couple more steps, including normalizing to get the probabilities just like before. And so we end up now with predictions. One difference here from what I described before is that with a transformer, we actually get predictions not just for the last token, we get predictions for all the tokens in the sequence. And then we can take the transformer and say, well, for all these tokens, these were the actual ground truth labels. So basically, every input token is used to influence the predictions, but it's also used itself as a target to train the model. This makes these models very efficient because we can basically take a whole sequence of tokens, get the model's predictions for all of these tokens, and then in parallel, train the model to improve on all of them. This is really a key point for why transformers have taken off as like the main language modeling architecture. We can train them very efficiently. But for the purpose of this talk, if you didn't get what I just said, that is just kind of a technical detail. Okay, so let's discuss the two different layers we see in the transformer. We have feed-forward layers. So feed-forward layers, again, they take our vector representation of all the tokens we have, and then act on them in a similar way to what we saw before. We have here I'm multiplying on the right. So we have the inputs X, we act on them token by token with a weight matrix. We apply a nonlinearity, which is pretty similar to the nonlinearity we saw before. Maybe ReLU, maybe something slightly different. And then we apply another linear transformation. And that's it. That's a feed-forward layer in the network. And we do this a bunch of times. And then we alternate that with the different kind of processing, which is the self-attention layer. And this is kind of where the magic happens with these transformer architectures. So I'm going to spend some time on this layer. So what's happening here is that basically we want the model to somehow process a bunch of tokens and then give us a good prediction for the next token. And to give a sense of scale, the number of tokens the model can see before the current token can be in the thousands. So it's a lot of information to kind of sift through to kind of inform the prediction for the next token. So what the attention layer does is it tries to focus on which of these previous tokens are going to be the most important ones for forming the prediction of the next one. And so what literally happens is that in the attention layer, the model calculates a weight mask over all the previous tokens. So it's a vector of numbers between 0 and 1 that sum up to 1 that supposedly, if all goes well, tell the model this token is the most important one, or these few tokens are the most important one for forming the prediction. And then they go through further processing to actually figure out the prediction. So the classic example of this is, let's say we want our model to translate from French to English. And so in French, the adjectives come after the noun. In English, they come before. And let's say we're kind of translating something that means yellow house from French to English, and we've already generated yellow, let's say. And now we're trying to generate house. So it makes sense for the model to kind of learn to figure out of all the text that it saw before, where is the noun that corresponds to house in French? And the ordering is going to flip from English. So we wanted to be able to kind of attend to any of the tokens before. If all goes well, the model will compute a mask that is peaked at the word for house, and then it will use that. It will say, oh, I know how to translate house to English, and it will do that processing. Concretely, the way it works is that for every output token here, let's look at an output token, it calculates a mask on all the previous tokens. We don't want it to peek into the future because we want to use it to generate text where we don't know what the future tokens are. So look at the past, calculate a mask, do some processing, and do this again and again at every attention layer. So that's at a high level what the causal attention thing does. Here are the formulas, just so it doesn't stay mysterious. The details here are not that important, but just so you see the full thing. So we have, again, this is the self-attention layer. So we have our inputs as before, the same thing that kind of makes its way through the network and gets processed layer by layer. We have a few weight matrices. We calculate these things called queries, keys, and values, which simply mean take the input and apply some linear transformations to them. These are going to be the weights that are going to be learned as part of gradient descent. And then this is where the key kind of thing happens. We take these queries and keys and we combine them, we multiply them to get a matrix that is T by T. So number of tokens by number of tokens. And then we normalize with the softmax function, which gives us like a probability distribution. So it ends up being that for every token, we have a corresponding row, which represents this mask, this weighted mask over previous tokens. Then we take this called the attention matrix, and then we take the attention matrix and we kind of apply some further processing on this thing called values. This is really the key point here is this attention mask, where every row for every token tells us which of these previous tokens are most important. Okay, so I hope this gives some sense of what transformer networks are about, how we train them, how we use them for inference. We're going to shift gears now and talk about more at a high level trends that we've seen with these language models, these transformer-based neural networks, and then we'll get to Minerva and see how we apply all of this technology to solving math and science problems. So one thing that we've seen with these models, as you see, there are many choices that can kind of go in when you build these models. We can choose how many layers we have. We can choose how many neurons per layer we have. There are lots of different choices that go into this. One thing that has emerged is that as we scale up these models, as we train them on more and more data, they get predictably better. This is work that was done a few years ago by Jared Kaplan and others at OpenAI, where they took a bunch of these models at various different scales and trained them on some scraped data from the internet like we described. And so every curve here is the training curve for one of these models. The x-axis is compute, that is how many flops we spent training the model, so that different models of different sizes are kind of all on equal footing. And the y-axis is the test loss. So this is the same loss that we talked about before, measuring in some rough sense the performance of the model, so lower is better. And it's test loss in the sense that it's evaluated on tokens that the model has not seen during training. So it's like evaluated on unseen data. And you can see that the shapes of these individual training curves is not that, there's maybe not a very simple form to it. But if we instead ask the question, for a given compute budget, what is the best performance we can achieve? Then let's say for this point here, it's going to be whatever model ended up hitting this line here and achieving the best test loss. We see that once we connect the line between these, we get a fairly clean power law that spans many orders of magnitude. And so that means that if we know how to properly trade off number of parameters and number of tokens that we're computing the model on, that we're training the model on, we can actually predict for a given budget what is the loss that we're going to get if we do the optimal thing we can when training. And so this is what I mean by getting predictably better results. We can predict what the loss is going to be, even if we increase our budget 10 times. These improvements in scale, they're not just quantitative, they're also qualitative. If you've played with these models, have kind of followed their progression, then you must have seen how the results get qualitatively better on text. We see the same on images. So this is an example of a model that was trained to do something quite different. It was trained to take in a piece of text as input and generate an image that corresponds to that piece of text. This also happens to be based on transformer architecture, but it's for a different domain. And this is work from Google. And you can see how, so you can look at the prompt and it says, so a portrait photo of a kangaroo wearing an orange hoodie, blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign that says welcome friends. And they trained models at several different scales. The number here is the number of tunable parameters in the model. And you can see how the 350 million parameter model does kind of an okay job. This thing kind of looks like a kangaroo. There is a sign, but the text is not legible. There's something in the background. It's not the Sydney Opera House. So it's okay, but like not amazing. And then you can see how increasing the number of parameters and also increasing the amount of data the model has seen really qualitatively improve the quality. At the end, you get a kangaroo. It is wearing blue sunglasses. There is the Sydney Opera House, and the text is fully legible, which seems to be the last jump kind of to happen. For some reason, these text-to-image models, they really struggle with getting the text right. And so we see these in the text models as well. So we know that scale helps, and we know that if we have a task that we think is hard and we try it out on a small model and we don't get what we want, it might be that if we just scale things up, we'll get really good results. It's hard to predict, but we've seen that happen again and again. And so that was the question that was our starting point for this project. It was, can we take these language models, which have proven to be pretty impressive on natural language and on code and on other modalities like vision, and can we apply the same to math and science? Which is considered a very hard domain for these models because it requires hard logic. It requires not making mistakes along the way when we are solving a question, which kind of conflicts with how these models work because they are stochastic at the end of the day. A whole host of skills that are not natural, or at least naively, it seems they should not be natural for language models. But we said, well, what if we try anyway? And what if we apply scale to it? That's really the thing that has not been tried before. And so our approach was, let's collect the biggest data set we can of documents that contain some kind of math, some kind of signal that corresponds, that might potentially help with solving math questions and science questions. And then take a large model and train it. In this case, we didn't start from scratch. We started with a model that was already trained on a lot of natural language data, and then we continued training it on using gradient descent on this large corpus of data. And then we sprinkled on top a few inference time techniques, which I'll describe. There's some more stuff you can do once you've trained the model to get better performance out of it. And before I go through that whole process, I want to show a couple of examples of what you get with this kind of model once you go through this whole process. So this is an example from a benchmark called MMLU. This is a very large benchmark of questions and answers. Includes STEM answers, but also things like history and other topics. Here, this is coming from the college physics section of this benchmark. And the question is, so we have a uniform solid disk starts from rest and rolls down an inclined plane without slipping. After some time, what fraction of the disk's total kinetic energy is rotational kinetic energy? And this is a multiple choice benchmark, so you get these multiple choice answers to choose from. And this is what Minerva, the model we trained, this is what it produced. And I want to emphasize that this is produced token by token. Just the whole procedure as I described it before is the same here. We take this as input, and then we start sampling from the model token by token, and this is what it does. And so it says the disk has both translational and rotational kinetic energy. It introduces some symbols for the speed and the moment of inertia and so on. And then it writes down the formula for the kinetic energy. It writes down the formula for the rotational kinetic energy. Here there is the moment of inertia, so it puts that in, which I had to check for myself is correct because I don't remember the moment of inertia for a solid disk. Simplifies things a bit and then says, okay, therefore the ratio is this, plugs in the formulas, simplifies, gets the 1/3, and then says, okay, so the final answer is B. And the format for all of this, here we rendered the answer. The format is LaTeX. So the way the model sees the input and produces the output is all in LaTeX. So it actually produces all of these LaTeX symbols, one after the other, and then we go and render it to make it look pretty. And you can see more examples of many other examples of Minerva inputs and outputs, including mistakes in the sample explorer here. Here's another question. This is from the math benchmark. This is a benchmark that's focused on math. Here it's not multiple choice, it's open-ended questions that result in some short answer. So that there are no proofs here. It's all questions where you calculate something and you end up with a number or a symbol. And this is from intermediate algebra, and this is from, so these questions have levels. They go from 1 to 5. 1 is like the considered easiest. So this is on the easy side on this benchmark. And so the question here is find the center of ellipse, whose equation is this. So this is the model's answer. So we have, it writes down the equation, and then it completes the square and goes through the steps of that, and then isolates, writes it, basically brings the equation to this form where you can read off the coordinates, and then it says the center of the ellipse is -4, 1, and this is the final answer.
How long does it take for it to do a question like that?
Like seconds, something like that, maybe less, yeah. Yeah, it's like if you've played with ChatGPT, it's like this model is bigger, so it's a bit slower, but it's like if you see how fast it's generating the tokens, it's the same idea. Yeah. Okay, so these are a couple examples. I'll show more examples in a bit, but let me go back to how we trained the model. And so it all starts with the training data. Yeah.
Could you maybe, if you'll come back to this, but those are two examples that work very well, obviously. Is there some like actual success rate that these things have?
Yeah, I will show that. I'll show some mistakes also. Yeah. Okay, so with these models, something that definitely took me a while to appreciate is that it's really all about the data. Like once you figure out the basic architecture, like as we discussed, like this transformer architecture, gradient descent, all of that, you can apply that to basically anything, to text, to vision, to many other things. But you need to get the data right. And that's also the hardest part. Like if you think about this from a theoretical perspective, understanding the data and what distribution is it's coming from and all that, that's kind of the most tricky part of understanding all of this. But to get performance out of it, you need the right kind of data, and you need a lot of it. So in this case, the data set included 60 gigabytes of documents with a mix of natural language and mathematical expression, and it came from 2 sources of roughly equal size in the data set. So one source is archive papers. It was all the papers in archive in LaTeX form with almost no processing, just the papers as is. So again, so when training this model, you take let's say a paper, you chop it up a little bit because the paper doesn't fit in the input for the model. So you need to chop it up a little bit, and then you take every substring in the paper and you say, here's the input, try to predict the output, and it's going to be the next token. So it's going to be either the LaTeX command or like the next word or number, whatever it is. And you do that again and again for all the tokens in all the archive papers. So that's one source. And the second source are all the web pages we can find that contain some kind of math in them. So if you've ever tried to put math on the web, you know, there are like 2 plugins that do this. There's MathJax and MathML. MathJax is essentially LaTeX. So in that sense, the formatting is very similar to archive. And so we took all the web pages we could find. We removed all the HTML tags so that it just looks like clean text with LaTeX. And so the documents we ended up with look very much like papers in the sense that they're just a mix of English and LaTeX commands. And that composed the whole data set. And then to train the model, we took an existing model at Google, which is the Palm model. This was a model, or it's actually 3 models that were trained on a lot of natural language data like Wikipedia, news, Reddit forums, things like that. There are 3 scales of models with number of parameters of like 8 billion, 62 billion, and 540 billion parameters, so like large models. And then we took them and fine-tuned them on this math data set that we have. And by fine tuning, I just mean we took the trained model, that's the set of all the weights after it saw a lot of natural language. And then we continued training it with this new data set, just continued gradient descent for a while. And you can see here the number of like how many training steps we had and how many tokens each of these models saw. To give a sense of the scale of these experiments, so the largest model here, the 540 billion parameters, was trained on 1,000 TPU chips. That's very similar to like 1,000 GPU chips or 1,000 GPUs for a month. So it's quite compute heavy. The smaller models didn't require as many resources. Okay, so that's how we trained the model. And the last thing is to actually get good performance out of these models. Typically, if you take a model like this and you just ask it a math question, it's not going to do very well. You need to add a little bit of what I would call alignment or a little bit, you need to do a little bit more inference time when you actually run these models to get performance, to get good performance out of these models. And the first thing that goes into this is called few-shot prompting. So here the idea is very simple. Let's say you want the model to act as a calculator and try to calculate something. You can go and ask it what is like 100 plus 15, and it will sometimes get it right. The way to get it to perform much better is to, in the input, show it a bunch of questions and answers of the kind you'd like it to answer, and then ask it a new question. That dramatically increases the performance of these models. So this is an example of when we try to see how good the model does on basic arithmetic, this is the prompt we give it. We always give it the same set of questions and answers. It doesn't matter what question we end up actually asking it. We don't need to tailor it to the question, but it just needs to have kind of the right format. And so this is what we ask, and then we do Q-call-in and ask it the actual question that we like. So that's few-shot prompting, which we use in all the experiments. The second, to kind of build on top of few-shot prompting, is what's known as chain of thought prompting. Yeah.
Or is that just the way you think you have to do it?
Oh, I think this is a typo. Yeah, there's no reason. Yeah, I think it's just a typo. Sorry. Good catch. Yeah, these are repeated. I never noticed that. Yeah, I don't think we had it. I don't think we had that in the original prompt. Okay, now, so if you want to have it do arithmetic, you can give it that prompt. It will do pretty well. But if you want to ask it a complicated math or physics question, and you just give it a few examples of difficult questions and the final answer, it will do its best to produce the final answer, but it will usually fail. It can't just like in one go, just like do the whole like, solid state or solid state calculation with the moment of inertia and so on, just inside the network. That doesn't work. Instead, we want to prompt it to try to give us a step-by-step solution. And if we do that, then the chances of it actually solving the question go up dramatically, because it will actually try to produce a step-by-step solution, and then hopefully will kind of guide itself to the right answer. So that's called chain of thought prompting. And the idea is just like few-shot prompting, but give it a question. And then for that question, give it a step-by-step solution, and do that a few times, and then ask it the question. If you show it these few examples, then when it tries to answer your actual question, it will also try to generate tokens one by one and give you the answer. So this is an example from the prompt that we actually use to produce math questions. It's always the same prompt. So we chose 4 questions on the math benchmark. We chose 4 questions at random. And we try different prompts. It doesn't really matter which questions you put in there, as long as they just kind of have the right flavor. And so this is the first one. It's like find the domain of this expression. And this is the solution from the data set, because the data set has solutions in it. So here's the expressions inside each square root. They must be non-negative. So there's some inequalities and so on. And this is the final answer. And then we end with, I hope it is correct. And that, yeah. And the point of doing that is that the model will then also say, I hope it is correct. And then we can find that string, and that helps us find where the final answer actually is. So it's just a way of, it's not to improve performance or anything. It's just a way to make it easier to parse. When did it actually finish generating the answer? And so this is the prompt we use. We have these like 3 more examples of this kind, and then we give it the actual thing we wanted to answer, and then we say solution, and then let it complete the rest. And the last inference time technique that we use is majority voting. And this one is I found pretty surprising. And the idea is this. So remember that when we sample from this model, we can sample with temperature. We have a choice of how to adjust the temperature, and higher temperature will give us more exploration of the answer space. And zero temperature will always give us the highest likelihood token. So we always get the same thing. So if we have one shot at it, we just want to generate one answer. The best thing to do is generate it at zero temperature. Just take the most likely token. That will give us the highest accuracy. But it turns out that there's a better thing to do if we're willing to spend more compute, which is take the model, sample, let's say 100 answers from it, then look, so each time, let's say this was the question, we'll get 100 different, with finite temperature. So each time we'll get some different answer with different chain of thought, and we'll get some final answer. Take those 100 and choose the one that had the most common final answer and take that as the answer. So this is called majority voting or self-consistency. This turns out to improve performance by a lot. It's way better to do that than to, if you're willing to spend the compute, than to just generate one answer with zero temperature. And you'll see in a minute exactly how much this improves performance. And this goes to something that is called it's a part of what's being called the capability overhang of these models. So these models, out of the box, they don't look very impressive. But once you do few shot prompting and you sample multiple times and so on, they can really give you much more impressive results than what it first appears, which means that they have these capabilities in them that we're kind of slowly discovering. Yeah.
So if you're sort of bucketing and finding those common final answers, that means that you have multiple models that are outputting maybe different text in the middle, but then coming out with the same final answer at the end. So
It's all one model, but the model is stochastic.
So but it comes out with some answer, and it might have some different sort of steps along the way to
Yes.
get the final answer. And then how do you sort of pick the right steps? Like you pick the model that has the best final answer by doing this method, but then each of the ones that gave a final answer might have different steps along the way.
Oh, we just choose one.
Just choose one.
Yeah, just choose one. I mean, this is more to evaluate, let's say, you know, if we just want to evaluate the accuracy, like how good the model did, we then for that, we don't care what the steps were, right? That's just to get the number. But if you want to actually present an answer, then yeah, we just choose one of them.
Yeah, I guess my question, so the accuracy is just sort of being tested on the final answer, not on sort of steps.
Yes. Yeah, and I'll show an example where that fails actually. Yeah. Yep. Yeah.
So just to clarify this, when you say it's stochastic, you literally, if you type exactly the same input, you will get two different answers. They're slightly different.
If you sample with non-zero temperature, you will get two different answers because we're sampling from a distribution, right? So yeah.
Okay, and is that what it means to say each has a different chain of thought? Or
Yeah,
is there
the tokens
something
will be
else?
different.
Does that mean something else? Like this? Each has a different chain of thought just means the process, the stochastic process of temperature leads to different answers.
That's what that means. Yeah. Okay, so a few more results and then I'll show aggregate results on the whole benchmark. So this is again on math. This is this benchmark that involves math questions. So here the question is, so a particle moves so that these are its coordinates at time t. Find the speed of the particle measured in some units. This is the target answer for reference. So the target is the answer. So when you have the benchmark, you get questions and you get full correct answers, not just the final answers, but you get whole like step-by-step answers. So this is the target answer. Parametric curve describes the circle radius 3. So it does something with this kind, and there was some figure in there that we drop. And so this is the speed of the particle. The model does it differently. So it says the speed is the magnitude of the velocity vector. So we must first find the velocity vector, which is the derivative of the position vector. So it writes down the derivative and then takes the derivative, simplifies a little bit, and then calculates the magnitude, simplifies, uses sine square plus cosine square equal 1, and gets the 3/4. So this is another example. And then here are the aggregate results on math. So what's going on here? So x-axis here are the different topics inside the math benchmark. So you can see there's intermediate algebra, number theory, and so on. If you want, it's just enough to focus on overall. So overall is just like the average over all the different topics. Y-axis is the accuracy. So for reference, the numbers I think were, so So someone who won, I think a multiple time gold medalist on Math Olympiads got like, I think something like 90% on this benchmark. And a student, something like a STEM student who wasn't very motivated to solve this, I'm quoting from the paper, it got, I think, like 60% or 50%, so something like that. So if you're motivated, you can solve it. If you're not motivated, then like you don't get very far. We don't have those numbers here, but on the right, you can see the performance of the different models. And I think we can, I mean, you can see, I mean, the three different bars correspond to the three different model sizes that we have. And so clearly, like, bigger models do better. No big surprise there. But you can see how a couple of the techniques that we introduced, you can see how the ablation of how they help. So this is all with few shot prompt or chain of thought prompting. If you don't do chain of thought prompting, you basically get nothing. But with chain of thought prompting, this bar is the PALM model. So that was trained on natural language, some math in there, probably not a lot. So it does about a bit less than 10% on this benchmark. Then the next jump comes from the extra training that we did on archive and math web pages and all that, and see that gives a significant bump in performance. And then you can see that adding this majority voting thing where you just sample multiple times and choose the most likely answer, that by itself gives you an extra like 17%. So it's not as much as training the model, but it's like with pretty minimal effort, you can bump up performance by a lot, which I think is a very interesting property of these models. Yeah.
For the majority voting, how do you know what temperature to use?
We tuned, so we tried, and so there's basically what you see is there's a trade-off from accuracy, but you also can calculate the entropy of, well, you can calculate the frequencies of the different answers you get, and you can calculate the entropy in that space of incorrect answers, how much you're exploring that space, and that goes up with temperature. And so it's like the trade-off between these two things that you can see very clearly. At the end, you end up with a very clear optimal temperature, which was like, I think for this was it was 0.7, I think was the final number. Yeah.
So like for a previous slide, it was like the X part and the mass X part of the X separate, or they were treating them as simple. So is this like some more like a mass? Is there like some sort of mass layer to do with this kind of calculation, or like they're just
No,
still?
it's all just LaTeX. It's all just LaTeX characters.
So they treat it as character basically as words.
As tokens, yeah.
Oh, excellent.
I mean, it's literally LaTeX. I mean, the output's LaTeX, just like that. There's no special math processing happening. Yeah, it's the same. It's like exactly the same as if you just take like something like GPT-3, just train it on different data, and it does this. That's all it is.
Your vision, like, it will be better if you can separate, because the text explaining part clearly has a different sort of flavor compared to this kind of pure math like this. Right? Do you imagine, maybe having like the network to have like this kind of true functionality doing this kind of things, or to expect SOTA standard is just just using language model for math?
I think this, my takeaway from this whole work is that this is better, because then the model can kind of blend math and English as it sees, and we don't have to worry about, oh, now we're switching to math mode, we're switching back from math mode. We don't have to worry about any of that. Like, otherwise, if we start, whenever we start, well, here's the trade-off. Whenever we start separating these things, we have to train the model to figure out when to use each module. In order to do that, we need to give it the data. Okay, now, instead of like a very large data set that we just throw at the model, we have to start going in there and do the feature engineering of like, here you stop text, here you start math, and do all of that, which might not be completely obvious, because sometimes you just have like numbers embedded in English with no LaTeX tags, right? So there's that just generates a lot of work. And if the model can do it well, as it seems like it can, then it's easier to just like not worry about it. Yeah, because if it works, it works. Yeah.
Can you give us a sense for the size of the window of attention of the maximum window of attention of the transformer? Would it be the whole essay here, or would it be a fraction of it?
Well, all of this fits. Yeah, it's 2,000 tokens. So 2,000 tokens includes.
Here we have about what, 700-800, give or take.
Less, I think it's less, it's gonna be less than that. I would say maybe 200 here, something like that. It does need to fit the prompt. I mean, that's kind of the tricky thing is we do need to fit these 4 questions with their answers in there.
Right, it was wondering, so it fits all of the previous 4 questions. Okay.
Yes, it fits that, and then it fits, it's enough to fit like a question like this. But if you start doing so, if you try to get it to write a paper or something, a paper would not fit. Yeah, more like I don't know, a few pages of a paper would fit. Yeah.
Question?
Yeah.
At what level does it figure out that sine squared plus cosine squared is 1? Is it because it read the Wikipedia article on trigonometric identities, or did you get a set of rules?
We gave it no set of rules. If you're asking me what was it that made it do this, I don't know. But we didn't show it any rules. Yeah.
So I think that's another way of asking it. It's completely probabilistic. So the reason that it's putting in what's like, I don't know my glasses, so I can't really.
Sorry.
X followed by Y. So the reason it can do that is purely because after building up this gargantuan statistical model, it says in this context, Y follows X.
Yes.
With high probability.
That's it.
So it has no, so it's completely, but this is completely correlated. This is correlation implies causation, basically, right? Because it's basically completely correlation. All of this is statistical correlation. And we look at it and go, oh yes, it knows something about the input because look, it's clearly given us meaning, but it doesn't actually.
Yes, I'm not claiming that it knows anything or understands anything. That is how I'm thinking about it. It's a purely statistical model. That's right.
No implication.
Yes,
good or bad. Just trying to understand like how can it do this, right? And because we think, wow, that's amazing, but actually it turns out a lot of statistics.
It's all statistics. It's all statistics. Yeah.
The questions that are within the 2000 tokens prior to this question, are they math questions or science questions, or they the ones you showed us previously? Yeah,
they're math. So when we do it on a benchmark, so we did it on like 2-3 benchmarks, we use questions from the training set of that benchmark. So when we ask these kinds of questions for math, then they will be, I mean, this is the first example of the question that we actually put in there. So there will be math questions. Yeah. On MMLU, so MMLU is another example where you actually then have like math and physics and biology and so on. And we tried giving it I mean, our prompt doesn't care about the subtopic there. We tried giving it a prompt from that subtopic. It doesn't matter. It does matter that it's multiple choice. I mean, that kind of gets it to do the right thing, but the topic doesn't seem to matter too much. Yeah. Okay, this one I want to show because I really like it, even though I'll run out of time. So a stone it's very simple. Okay, so a stone is thrown horizontally with some initial speed from a bridge. Find the stone's total speed when it enters the water, right? Okay, so multiple choice question again, and the model does, so since the stone is thrown horizontally, this is the speed. After 4 seconds, its vertical speed is this, and it uses 9.8 meters per second square for the gravitational constant, even though you can see from the possible choices that the intent is to use 10, right? Like you do in like up to some point in your studies, you use 10, I guess. But it does this, and it gets it gets the numbers, and it says, okay, square root vx squared plus vy squared, and it puts in this number, and it's like, okay, I need to fit it into this. So this is like more or less 50 meters per square. So that's the answer. So I thought that was cute. Yeah. Okay, we'll skip this. Okay, results on MMLU. These are again some results on the other benchmark. I don't think we have much more to learn from this. I want to show the mistakes. Yeah, the mistakes are more interesting. So there are all kinds of mistakes that the model does. You see, I mean, the performance is not 90% or 100%. It's like 50% on math. So there's a lot of room for improvement. Here's an example of a calculation mistake, and also kind of shows why it's tricky to find these mistakes in the chain of thought. So figure skater is facing north, and then spins 2250 degrees. Which direction Okay, and the answer is facing south, spins 20 to 50 degrees, which is 5 360-degree rotations and 150 degrees. That's not correct. That's just wrong. And it wouldn't, I don't think this would even lead to south anyway. So the whole thing is just wrong. But it's very interpretable. I think the nice thing about this is you can read the answer and kind of figure out, okay, there was a calculation mistake happening here. Here's another example. So what is the largest 3-digit number in which the product of digits is 12? Okay, so it starts off by saying the largest 3-digit number is 999, which is true, but like not helpful. And then the prime factorization of 12 is 2 to the power 2 times 3. This is something that for some reason this model really likes to do. It really likes to solve questions by giving you the prime factorization of numbers and then saying something about the factors. I don't know why, but this happens a lot. And then it says the digits 2 to 3 will work, which they won't, but the largest 3-digit number will be obtained by choosing the largest digit for the hundredths place. So it puts 9 there. This is all wrong. So, but here, I don't know, I wouldn't call it exactly a calculation mistake, more like a reasoning mistake. So that also happens. And then the last mistake I want to show is these false positives, which do happen at a rate of about 8%, where the model gives an incorrect chain of thought, but ends up with the correct final answer. This happens. Find the smallest positive integer k such that for every positive integer n, 6n plus k is relatively prime to each of, I can't see this, there you go, 6n plus 3, 6n plus 2, 6n plus 2. So there's a lot going on here. The answer is, well, you can kind of guess at the answer. The answer is 5, because if you put k equal 1, 2, or 3, then it's going to be not relatively prime to any of these numbers, to one of these numbers, because it's the same number. If you put 4, it's an even number, so it's not relatively prime to this even number. So 5 is the first thing that could work, and it's going to be 5. But you can see what the model does is it says, okay, we have these 3 GCD equations, which so far so good. But then we cancel out the 6n terms, which is, you can't do that. And then it doesn't even cancel them out. And then it just goes off the rails, but then ends up with k equal 5. So this happens, and that's pretty weird. Doesn't happen that often, but it does happen. So these are, this gives a flavor of like, you know, when it makes a mistake, you can figure out, I mean, it's like, you get an answer and you can see where the mistake is, and you can see what kind of, it is interpretable with lots of mistakes still. Yeah.
Do you just estimate the rate of false positives sort of by hand by looking through some subset, or is there?
Yeah, we went through like a couple hundred examples to estimate. Yeah.
When there is a mistake, is the generated probability lower, so the likelihood lower? It's kind of like we can ask how confident he is about it.
Yeah, that's an interesting question. It's like the question is how calibrated are these models, in the sense of is the probability they send to an answer correlated with the actual probability that they got it right? We didn't test it on this model. There is evidence that the larger models are also better calibrated. So somehow scale also helps with calibration. But I will be surprised if it holds for these very long, complicated chain of thought answers, because then it's also a question of what probability are you calculating this on? Is it the probability of the whole sequence? If you just calculate on the probability of the final answer, that's not a very good indicator, because that's conditioned on the previous stuff that the model did. So it's kind of a tricky question to answer, to measure, a tricky thing to measure with these like very long involved answers. Yeah.
I'm assuming this is a non-zero temperature, right? For this false positive. So is it possible that out of 100 possibilities, it came to this answer, but like the other 999, it had the right train of thought?
I mean, that could be. I don't remember the temperature for this. I don't remember the temperature, but you could get this with 0 temperature. Yeah, I wouldn't be surprised. Yeah, this can happen. Yeah.
My question is, when you train the model with like self-consistency checks, do you also change the name of variables to like train the model to think like abstractly about each variable?
No, we don't change anything. No, we just use the same. Yeah.
And my other question is, how do you stop the model at the end? Like, how do you teach it to those like stop at the end?
We wait for it to say, I hope it is correct, and then we stop. That's it. Yeah.
Is there something qualitatively different between this kind of problem and designing an experiment or writing a proof, or do you see it as a matter of scale?
you want data. We have lots of data for this. If we want something to help us design an experiment, I'm not, where does all the data come from to say, this is my set of circumstances and I'm going to design that experiment? I'm not sure where that data will come from. Writing a proof is definitely within scope for this kind of stuff. It's just that for us, it's very nice to have a short final answer to evaluate so we know if it's correct or not. With proofs, it's much harder to know if they were correct or not. So it just makes evaluation harder, but proofs are not, I don't think proofs are like, yeah, I wouldn't say proofs in general are more difficult than doing like solving a physics question. It's a matter of how hard is it. Yeah.
I have two questions. So one is actually related to what you just said. There's software in math for evaluating proofs automatically, right?
Yep.
So has anybody looked at doing this, having something generate proofs and it might generate garbage, but you can check them automatically?
Yeah. So there's a paper on this actually. So what they did is they took from Tony Wu and others. So they took the proofs that the model outputs. I think they did this on Minerva, maybe on Codex. So they took the proofs that the model outputs, and then they asked the model to translate that proof into code that you can run through a theorem prover.
Good.
And it works sometimes, and then it gives you some signal on whether it's correct or not. Yeah.
And then, do you have any, is there any maybe naive expectation or more rigorous statement about the level, if you have if you train a model on some canon, what's the maximum accuracy? Like I imagine if you gave it, bad data, it will not give accurate results.
Mm-hmm.
Is there any way to kind of pre-assess how accurate you would expect the model to be?
Only in this very aggregate sense of the loss that we can predict. If we run a few small scale experiments, the power law will be very clean and we can predict the loss. On specific tasks, or if we're talking about accuracy or things like that, we don't really know how to predict. It's not as clean as this.
Yeah, so when we train human, we use much less data.
When we train what, sorry?
Human.
Sorry?
Human.
Oh, yeah, sure. Yeah.
So basically the 50 gigabytes.
Yes.
Are there any research ideas for improving the network with much less input data?
There's lots. Yeah, we keep making these things more and more efficient. Even since Palm came out, folks at DeepMind figured out a way to make the model 4 times smaller to get the same performance with the same budget. So this is very active. Basically what happened was we scaled things up as much as we could because it looked like it would give benefits. We're getting nice results. And now a lot of the work goes into, well, people keep scaling it up, but also trying to make it as efficient as possible. Yeah.
Is it possible to have like very big model, but very little? Because this picture shows that when you increase the model, you also need more data.
There is a trade. Yeah, that's right. So our best understanding right now is that the best thing to do is increase the number of parameters and the number of tokens linearly with a ratio of about 20. So it's about 20 tokens per parameter. And the fact that we increase them linearly seems to be a very universal result. The actual ratio, is it 20 or 15 or 25? That seems to vary by data set. But that is our best understanding right now of how to optimally scale these things. It's still like orders of magnitude less efficient than a student, for sure. I mean, obviously, yeah.
Just some idea of how it manages to even simple things like doing algebra. Right? You wanted to multiply 2 numbers together. Presumably, I've seen many examples of Python 3, but I've never seen the particular example you show. How does it manage to get the answer?
I don't have insight into that, but this plot is maybe a little bit relevant to this question. So this is performance on basic arithmetic. So addition, subtraction, multiplication as a function of the number of digits. And this is with few shot, no chain of thought or anything. Just you showed a few examples and then you ask it and see if it does it or not. So you can see, let's say on addition, it can do like 8-digit, 9-digit addition at over 80% accuracy, which is better than I can do. And it's like doing it in your head. It's better than I can do. But with all these things, if you keep pushing the number of digits, it will deteriorate. So it's not like, it doesn't seem like it learned how to do long addition for everything it's seen and is then doing long addition for, it's not that. It's some fancy combination of pattern matching, and sometimes it gets the carry right, and sometimes it's, but you know, lots of memorization probably, and some soup of complicated things that lets it do that. It's not like it learned to do long addition. This is not what's happening.
Last 5 minutes, so
Yep.
let's go toward conclusion of the program, and then maybe take a couple of questions.
Yeah, I think I can skip the rest here. We're at the end. All right. So yeah, so I can just summarize. So training models on large amounts of math focused data, you get good performance on math and science questions. I think that's like the main takeaway. And for practically speaking, there is this capability overhang of these models where you can take them out of the box and do something and they won't do very well. But if you add things like few shot, chain of thought, majority voting, and probably other things that we don't know about, RLHF is another example of this kind of thing, you can get a lot more performance out of them. And yeah, that's it. Thank you.
It looks like there is a pattern in solving these problems in which you have to imagine an approach out of many, and there are many that will yield results and many that won't. And so the first thing that the network has to do is to decide in which direction to go to solve the problem, and then, so in some sense it's like an induction step, and then it does an induction step that tries to compute from that idea the solution. And so it would be interesting to see a sampler of situation when we got it wrong to see if it's mostly lack of ability of guessing what's the right approach. And so it started with a very unproductive approach that didn't get anywhere. And if you fix that, then it will deduce correctly or not.
Mm-hmm.
And the second question is, I imagine that there is a long-tail distribution of the yield approaches in some ways. Some approaches work very often and some are needed only a few times. And so it would be interesting to see if it's the most common approaches that get used and the ones that are not there.
Yeah, that analysis, that's interesting. We did not do that analysis of analyzing the chain of thoughts in that sense. I can't say about the mistakes. It's mostly like either it got one of the logical steps it got wrong and then went off track, or it got some calculation wrong, like, you know, it needed to multiply some numbers and got it wrong or something like that. That's like the vast majority of mistakes are of these kinds. We also have the next category, I guess, is these cases where it just clearly kind of, it misunderstood what was being asked. So it like answered a different question or something, but it's by far, it's not, I haven't seen many examples where it kind of went down some rabbit hole of like a completely incorrect approach. But that's also a function of the difficulty of these questions. Like if we now start asking it like IMO questions, right? Math Olympiad questions, where this planning step is much more significant and it's not as straightforward to get to the answer, I'm sure we'll see a lot more mistakes of the kind that you're describing. Yeah.
Yes, in the back. Yeah, you. Yep.
So where do you see the future improvement of this model can come from? For instance, is it from like better tuning of the model, or like larger model, or different model, or like larger data set, or where do you think is the future direction?
Yeah, I mean, there are more, it's not like we exhausted all the data sources with this. Like, for example, I don't think there's a lot of textbook data here. I mean, there was some textbook data in the pre-trained model, but not then the continued training, we didn't have any textbooks. So there are more data sources. I think that, I mean, now we have models that are generating their own training data. So once you get the model to some baseline level of performance in, let's say, solving math questions, you can use it to generate new solutions and somehow find which ones are correct with some probability, and then add them to the training data and continue training that way. So that can give us improvement that go beyond like the original data that we had. And that general technique of models improving themselves does seem to work. So you can do that on these kinds of questions. You can do it on like theorem proving style questions. I think that's where a lot of the improvement is going to come from, beyond just like showing it more data.
So what is the aspect of theoretical work? So far it seems like experiment, exploration, Yeah. So do we expect to see some theoretical understanding? So for example, you had linear property, linear behavior of the number of tokens versus parameters, etc. Are there like fundamental, do you expect to have some fundamental understanding of these things?
The understanding is improving. So now there are works that have some simple toy models around the dynamics. It's more about, I would say probably the theoretical understanding is going to help us figure out how to be more efficient when training these models, just like that work. Okay. And so there's this work called mu parameterization, where what they're doing is there is some simple model of the dynamics of gradient descent. And then it tells you, okay, you're going to train some small models to figure out the best learning rate. But then because of the way it's set up and the theoretical understanding, you're basically guaranteed that when you scale up the model, it's the same best learning rate. You don't have to look for your best learning rate again. So, if we can do that for all of these different model parameters, then it becomes more efficient because we don't have to go and search for them at the larger scales, which is very expensive. So that I think is the area where like theoretical understanding can currently help the most.
I can take one more question. Are you all satisfied? Yes.
Yeah, can you using computer to generate a lot of correct answer like addition, then this feed that into your training, then you improve the performance of addition.
Yes. The issue with that, you can do that. You'll very quickly get a model that's really good at addition on the distribution that you showed it. So let's say you generate samples up to 10-digit addition. It will be really good at things up to 10-digit addition. But if you then ask it about 30-digit addition, it will fail very, very quickly.
I see. So one needs some kind of theorem built into the model.
Yeah, we don't know how to do that. It does not extrapolate outside of the training distribution. Yeah.
Okay, thanks, guys.